you should get, for velocity, I didn't show the work. You should get for velocity 9.8 t plus vi. And then for the second part, I did show the work. To do the next part, I write velocity is dx dt. For velocity, I replace what I already have. Multiply by the dt, integrate both sides, plug in my limits, and I get x is 1/2 times 9.8 t squared plus v initial times t plus xi. Okay. This equation, I think, probably looks familiar to a lot of you. This equation is only correct for the special case where the acceleration is a constant. If that 9.8 changed to a 12, it would be okay, because 12 is still a constant. It'd be okay to just modify that to a 12 and that to a 12. If the acceleration we wrote as a variable like ac for a constant, I could replace this with a constant, and I can replace that with a constant. However, if the acceleration changes to something that's not constant, like 2v, it would be wrong to replace it with a 2v, and it would be wrong to put the 2v in like that. Okay? So those equations are only correct if acceleration is a constant. You cannot fix them by putting in your expression for a in for the acceleration in that equation. It does not work. In fact, what I'd like to do next is the case where acceleration is 2 times the velocity. It's my next example. Before I do this next example, though, I'd like to talk about how this next example might show up. My first example, although mathematically very easy to do, is actually the most contrived. Acceleration isn't often going to depend on time. Like you're driving your car, and your car's acceleration depends on the time on the clock. The car's acceleration is going to depend on your foot pressing on the pedals. It will depend on forces in the engine. It's not going to depend on time. There are some cases where acceleration depends on position. An example of a case where acceleration depends on position would be a mass connected to a set of springs. Depending on where the mass is located, the spring will pull with a different amount of force. So the force on the spring will depend on the position. Because the forces will depend on where the mass is located, then the acceleration would depend on where the mass is located. So anything involving springs is going to have an acceleration that depends on position. Or in other words, the acceleration can be written in terms of x. Sometimes the acceleration depends on how fast the objects go. An example of that is just dropping an object. If I drop an object, there are 2 forces acting on the object. When the object is in the air, can someone name one of the 2 forces acting on the object? Gravity going down.
Air resistance.
The second one is air resistance. Which of those 2 forces depends on the velocity? Air drag. The faster an object moves, more air drag or less air drag? More air drag. Okay, so the faster something goes, the more force of air drag you're going to have. You can all just experiment with that. Put your hand outside the window when you're driving. You can feel the force of air drag pushing back on your hand. Walking across the room, I can barely feel it. I can feel it just a touch. A little breeze on my face. I can't feel it much. So air drag force depends on velocity. So if the force depends on velocity, then the acceleration that you get from F equals ma is also going to depend on velocity. So this is a more normal situation. Acceleration depends on velocity. The previous example, acceleration equals 2 times the time, is more contrived. That's a situation that you're more likely to have as a textbook problem in dynamics class than you are in the real world. Nonetheless, it's a good textbook problem in dynamics class because it's a little bit easier to do than this one. So it's a good one to start with and master that first rather than going straight to the harder one. So let's now look at this one, the harder version. The acceleration is equal to 2 times the velocity. I have the same goal.